Then this is a BMW, the charger, wireless charger built by a company called Brusa, White City. And then you have Audi. It also comes with wireless charging. This is it was implemented almost like 10 years back, or something 8 or 10 years back, by KAIST, Korean Advanced Institute of Science and Technology. They demonstrated 1 megawatt power transfer for railway application. Then this is a conceptual diagram for wireless charging of electric ferry, where you have the sea wave, right? So you have your electric ship is shaking a lot, and it's not possible in a limited time frame to plug the to insert the plug of the charger to the socket of the uh, electric ferry, right? So here in this case, either one has to be patient and it takes a lot of time to initiate the charging process, or one can use wireless charging. So here is the concept, and there has been implementation of practical implementation of this wireless charger in some of the European countries such as Norway. Right? And this is the very old picture. Again, 10 years back, this was uh, implemented. It's a 200 kilowatt wireless charger by Momentum Dynamics. Back then, it was a startup company, and sorry about that. So they demonstrated for the electric bus 200 kilowatt charger. Let's go into the principle and components of wireless power transfer. So let's say you have two coils, which are magnetically coupled, right, but electrically decoupled, right? There is no physical connection between these two coils. So if we excite the primary coil with a time varying current, obviously you will have time varying flux, right, by Ampere's law, surrounding this coil. And if there is a second coil which intersects that time varying flux, obviously there will be induced EMF across the terminal of this coil by Faraday law of electromagnetic induction. Now, since there is a large air gap, obviously all the flux generated by this current will not couple the secondary coil, because there will be leakage, right? So coupling coefficient in this case is very poor. It's for wireless charging, depending upon the air gap, and especially when talking about electric vehicle, air gap should be 15 to 20 centimeter to respect the ground vehicle clearance defined by the uh, um, transportation authority, or those country rules, right? So the coupling is very poor. It's in the range of 0.1 to 0.3 maximum, right? No matter how well your coupler is designed for air gap targeting 15 to 20 centimeter, 0.3 is the best coupling you can achieve, right? And therefore, to compensate for the poor coupling, these coil are not used just like this. It's not an inductive coupling. We don't use inductive coupling for high power transfer at large air gap. We need to use resonant inductive coupling, right? And for that purpose, these capacitors are used, and these capacitors may be connected in series with the primary coil here, right? Or it could be connected in the parallel of the coil, like this picture here. And so you have four possibilities: series compensation, then you have the series parallel compensation, and parallel series, and parallel compensation. So you have the series parallel and parallel compensation. Now, this is a generalized block diagram of a wireless power transfer system or EV battery cell. So on the ground side or the way side, we have our transmitter. So this is the transmitter of our wireless charger, and you can see it consists of a coil, compensation capacitor, which could be just a capacitor either connected in series or parallel, or it could be a multi-resonant topology. So in previous slide we saw the four basic topology, but there are multiple way to minimize the effect of poor coupling, and multiple resonant topologies are used. So we could have one capacitor or many capacitors connected in different network to give more complicated compensation topology. Then you have the high frequency inverter. So what it does, so you have 50 hertz coming from the grid, or let's say you have the DC supply coming from the DC power supply. So this high frequency inverter convert the low frequency AC into high frequency AC output. Obviously, if there is grid, you will have your front end converter, which consists of your EMI filter, power factor correction stage, and so on. So you have your high frequency inverter, which convert your DC into high frequency AC, or 50 hertz supply into, let's say, 85 kilohertz of high frequency AC. And then to compensate for the poor coupling between primary and secondary coil, you have the compensation capacitors. Let me read and then, because of high frequency time varying current, you have high frequency flux surrounding this coil. And if there is a transmitter coil, a receiver coil, the receiver coil couples with or intersect with this time varying flux, and there will be voltage induced across the terminal of this secondary coil. Now, this voltage, again, there is a compensation capacitor, and the purpose of this compensation on the receiver side is to improve the power transfer capability. So compensation are used for two purposes, and depending on the primary side and secondary side, each serve a specific purpose. Primary side compensation makes the primary voltage and current in phase, so to minimize the reactive power drawn from the supply and drawn from the inverter. And secondary compensation is to boost the output power generated by this secondary coil, right? And both of them together ensure that the effect of overcoupling is minimized. Now, this is high frequency AC, which obviously cannot charge the battery. We need DC, so there is a rectifier. And then you have your EV battery, which is charged by this charger. So this whole thing is charged. Now, some of the components I have not shown here. It's not possible to include in the block, but are integral part and necessary for the functional aspect of this, or practical aspect of this wireless charger, which is foreign object detection system. There will be obviously communication interface between your primary and secondary coil. There will be coil detection system, so that vehicle will, so transmitter will know that there is a vehicle which needs charging, and then only it will initiate the power transfer, right? And then you have the shielding, because there's a large air gap. This flux can go anywhere, and it could be really harmful to the person fitted with a pacemaker or flux sensitive or magnetic field sensitive devices, right? It can also cause unwanted heating of the tissues in a healthy person, which may lead to the health issues, right? So electromagnetic shielding is required. And then there is a front end converter, which obviously, if you have AC, should be here. Now, as you can see there, to build a wireless charger, you have a lot of focus area. You have the coils, you have the converter, right? Then you have these functional safety aspects, foreign object detection system, coil detection system. Then you have the communication interface itself, which is challenging, right? And each of these blocks is a research topic in itself, require a lot of careful design consideration. So Just to give you an example, power converters which are used for IPT, there are number of possibility as you can see. So we have dual stage converter. Dual stage converter means we have AC, right? Then we convert the AC to DC, and then DC to back again high frequency AC, right? So it's a two-stage conversion, AC to DC, and then DC to high frequency AC. But in single stage, direct, there is one stage which convert the low frequency AC to high frequency AC, which we can fit to our. So in dual stage converter topology, you have two possibility: voltage source inverter, then you have the current source inverter. Again, in voltage source inverter, you have buck topology, you have the half bridge and full bridge. For current source, you have the push pull, half bridge, full bridge. Similarly, for the single stage, you have the matrix converter, then you have the bridgeless boost and voltage source inverter integration. And so this is just to show you that there are number of possible converter topology which might fit into your design or requirement, right? Now again, like I said, compensation also, I showed you the basic compensation, series, right? And series, parallel series, but there are many more. For example, you have multi-resonant topology. So this is your main inductor coil, and then you have LC uh, uh, resonance here. So it's called LC compensation. Then you have LCC because you have two capacitors used and one extra inductor. And then you have CLC because capacitors, then inductor, then capacitor is connected. This is the main coil, like that, right? So multiple possibilities are there for the compensation also. And for control, which we will see later, we have again multiple possibility because it's a coupled inductor. So to control the voltage and current to the battery, we can control either from the secondary side by controlling the secondary coil voltage and current, or we can control from the primary side by controlling the primary side voltage and current, or we can go control both sides also. So again, there is different possibilities for control. So these all things make the design a little bit complicated. Now let's see one basic topology, series topology. So you have your full bridge inverter here, which convert the DC voltage into high frequency AC. Now your AC is in this form, right? You can see this is square wave. It will obviously contain a lot of harmonic, but because of the resonance between the primary coil and the capacitor, it acts as a band pass filter, and your all the harmonics are eliminated, and you get almost pure sinusoidal current flowing through the. Similarly, same thing happens in the secondary sense. So here also you have very sinusoidal profile of the secondary current. Now you have a rectifier which will convert the voltage, this voltage, into DC voltage, which will supply to your load, which could be your EV battery, like this. So let's see the different planar coil shape used in the wireless power transfer system. Okay, so we need certain coil geometry which we can integrate into the vehicle. So you can imagine this is your vehicle like this, right? You have your vehicle like this. Now you have to install your transmitter coil. Obviously, it would be best that we could install it underneath the vehicle, right? And for that, we need some kind of planar coil geometry. We cannot go for this kind of coil geometry because obviously it will occupy a lot of space. It will compromise the ground vehicle clearance also. But this one, this is the top view. But if we see the cross-section view, it will be thin like this, right? So this can be integrated in the chassis of the vehicle, right? So there are several evolution of the planar coil throughout the time, and almost all were designed by one particular research group in New Zealand, Grant Kovich of University of Auckland. So this is the circular charging pad. Then this is your H-shape pad, also called flux pipe. And then you have your double D, because it looks like a D shape, right? So you have like this double D structure, and then you have double D, but with one extra coil. It's called the quadrature coil, and this shape is called double DQ, for 2D and 1Q quadrature coil. And then there is a slight improvement of this coil shape in the form of bipolar pad, in which two double D coils are overlapped. So we don't need one third coil. This overlap itself create a quadrature coil shape, right? So these are the popular coil topology, out of which this is the most popular, and this one is also used, but this is not very advantageous. We will see later. So let's understand the definitions. Some definition first. One is the parallel component, and there is the perpendicular component. So flux is originating like this. So this has two components. One which could be perpendicular to the surface of the coil. So we call it perpendicular component, and one which is parallel to the surface of the coil. So we call it the parallel component. And any flux component can be divided into these two components for all the planar pad, right? And depending upon which component is dominant, we will call it a pad which generates perpendicular component or parallel component. But remember that both components are present, but essentially we are calling a pad with which can generate perpendicular component. We mean that perpendicular component is the dominant component and parallel component is not dominant. So let's see the merit and some shortcomings of the circular pad. So one of the biggest merit of this coil is that same tolerance to misalignment in all directions. So this coil is non-directional. It's easier to operate. So you can imagine this is circular shape. It's a very symmetrical shape, right? So if this is your transmitter, right? So your vehicle could approach from any direction, either this direction or this direction or this direction, right? So no matter, you can approach to the transmitter coil or charging base or charging station from any direction, and you will have same amount of coupling, right? It is perfectly aligned. So this does not require a very complicated coil detection system. A simple camera based or some RFID based sensor is also enough for driver to park his car in close vicinity or in alignment with the transmitter. Right? It's also very easy to fabricate. It's based on the Archimedean spiral, which can be designed using mathematical equation. And so design is easy, right? Manufacturing cost is also easy, right? It's just a Archimedean spiral. So there are winder which can wind it based on your design of number of turns and outer and inner diameter. And it does not, it has a single-sided flux generation characteristic. So let's say this is the cross section of the coil, right? Now behind it we have the ferrite. This is the copper. This is the coil essentially. And this is your ferrite. And then you have the shield, aluminum shield. So flux essentially goes in the air like that, and it has to return from the back of the coil or pad. But because of the ferrite and the aluminum shield, or aluminum or copper is used as a shield, generally aluminum is used because it's cheaper. So it catches the flux and does not allow it to go like this. So you have very less leakage in this, right? It's a single-sided. All the flux are above the pad and very few behind the pad or from the side of the pad. So this is widely used for its simplicity. And its shortcoming is that it's non-polarized. Non-polarized means it can it can generate and couple vertical component of flux only. So only perpendicular component is dominant in this, right? And so for that particular reason, it is not interoperable with DD pad and HSEP pad in centrally aligned conditions. So remember that a perpendicular component of flux will interact with a pad which can generate a perpendicular component. So DD pad in perfectly aligned condition, dominant flux component is perpendicular, is parallel. So it is not interoperable. So let's say your car is fitted with double D pad but transmitter is circular pad, then you can obviously not charge it. So that is one demerit of this coil, right? And another demerit is fundamental flux height is 1/4 of the pad diameter. So let's say your coil, your pad cross section is of 1 meter. So this is the circular pad and diameter is 1 meter. Then maximum height of flux will be 1/4 meter only, right? So let's say you want to design a coil which can operate at 20 centimeter air gap. So you need a circular pad of diameter 20 into 4, right? So 80 centimeter. So in another word, we can say for a given air gap, size of pad, if it's made using circular pad, will be larger compared to other pads, right? So that's one demerit of this coil. And also another demerit is that it exhibits a null in the magnetic profile when offset by 40% of pad diameter or 70% of coil diameter. So in, let's say, throwing flux in the So let's say this is the transmitter coil, and this is the axis of the transmitter coil. Now its diameter is, for simplicity, I will keep it 100 centimeter. 100 centimeter. Now the receiver coil which is on the vehicle, if it's perfectly aligned, then it's fine, right? But let's say alignment is like that. Car owner didn't park his vehicle properly. So now the axes are offset by 50 centimeter, right? Now this will exhibit a null in the coupling profile when the offset is almost 40% of the pad diameter. So obviously, EMF induced in the secondary pad will be 0 in this case, right? The offset cannot be greater than 40 centimeter. So that's it has a limited charging zone, you can say, in elemental. So it's not very much suitable for in-motion charging. For in-motion charging, obviously, car is moving, so you need a pad which can give you a wide charging, right? Now this is the H-shaped pad, and this H-shaped pad is essentially a solenoid. So one advantage is that it can throw flux almost 2 times higher than circular pad. So in that sense, it is better than the circular pad. It's also very easy to design because the solenoid equations are well known. You can do analytical design. It's possible in this case. But shortcomings is that high eddy current loss in the aluminum backplate because it's a solenoid, so it generates flux on the top side also and bottom side also, right? So if you add the shielding, there is so much eddy current loss in this shell, aluminum shell. So it's less efficient compared to a circular pad of same size, right? And it's also costly, right? Because you have to use the solar ferrite in the form of this plate. Where in case of circular pad, we see that we don't need entire coils to be covered by ferrite. We can use instead a spoke-based arrangement, which has been proven to be very effective in minimizing the leakage flux. So spoke kind of arrangement we can use instead of going full ferrite, right? So this is not interoperable with the circular pad because main dominant component is the parallel flux, not the perpendicular flux. This is a double D pad. So its merit is a single-sided flux generation, just like your circular pad. It only generates flux on the top side like this. So the returning flux is caught by this ferrite spokes. So there is very less leakage. Flux height is also good. It's double the circular pad. It has high tolerance to misalignment along the width of the pad. So this is the width. So if a second receiver is parked like this, it will still have some coupling to charge the waking. So it has good tolerance, but only along the width, not along the length. Right. Shortcoming is that there is again existence of magnetic null when the offset is 34%, which is less than the circular pad. And it's again a polarized pad, so it can generate and couple only parallel component of flux. So parallel component of flux is dominant, perpendicular is not dominant, so it is only interoperable with the pad which can generate parallel component of flux. Right. You have double D and bipolar pad, both are same. Only thing is that just the double D coil which we saw can generate only parallel component. So to solve that, they added one quadrature coil, or you can say square coil, which is similar to the circular coil. It can generate perpendicular component. So you have both perpendicular component and parallel component of flux. But now you need two inverters, right? Because you have your double D pad and then you have quadrature coil. So to excite it, you need two inverter, and if you are using at a receiver, you need two rectifier, right? And control is little bit complicated, but it solves the demerit of your double D pad. It's also interoperable with all kind of pad. Now, in line of this innovation, they removed this quadrature coil and instead they overlap to double D pad. So this overlap itself creates a quadrature coil. So this solves the problem of having extra copper in the double D, right? But again, this one also requires two inverter, right? So these are the demerit of this pad. Then there is another coil, say called tripolar pad, and it needs three separate inverter, right? Or you can use a three-phase inverter also. But again, cost is high in design and also in manufacturing, or also control is little bit tricky. Now let's see example of how to design a circular charging pad. Right? Because some analytical calculation can be used for circular charging pad and flux pipe. For other coil shape, you have to rely on FEA tools, because analytical closed form solution is very, very, very difficult. So to design circular charging pad, we have five possibility. So coupling is a bilateral circuit property, right? So primary, you can see is same in all, but secondary, for the same inductance, you could wind it using same outer diameter, right? Or you could wind it where outer diameter is less than the outer diameter of your primary, but inner diameter is greater than. So like that, you have five possibilities. For same inductance, you can wind a circular, or you can create a solenoid, or you can create a spiral with number of possibilities depending on how many number of turns you are using, what is the internal spacing, right? So there are five possibilities. So to compare all the five possibilities, let's take a case study of 500 watt system operating at 40 kilohertz. So to deliver 48 volt output, so these are the calculation, right? And as per calculation, inductance of the primary coil should be this much, around 721 microhenry, and inductance of secondary should be 73 microhenry. And these calculations are done for series compensation topology, right? And for 40 kilohertz and 500 volt output. So essentially, we did the analytical calculation. We calculated how much inductance we would need for this particular voltage output and this particular output power and this frequency, right? Now, once we have these numbers, we can wind our coil. Now, how to wind it? So we first need to calculate. We have the numerical value of the inductance, 721 for our primary. So how to calculate the outer diameter, inner diameter, number of turn, and interturn spacing to get this value. So for that, we have very age-old Wheeler equation. So, and it's given by H.A. Wheeler, right? A lot of book and publication from this side, and you can calculate the inductance, and you get a very accurate estimate based on this equation. And using this equation, you can modify it little bit to get your outer diameter also, right? So you get the design of your coil part, right? Now, based on that design, you can fabricate all the 6 coil. So one primary and 5 secondary, right? So you see, inductance is same for all the secondary, but they are all physically different from each other because they have different number of turn. They may have different different inner and outer diameter relationship with respect to the primary. Now, how to decide the air gap between the coil? So that you can do calculate using this mutual inductance formula. This is using Biot-Savart law. You can calculate the mutual inductance at a particular point for a given spiral. Now, modifying this equation, you can calculate for this Archimedean spiral how much will be mutual inductance between these two coils. So this is also possible. So here is a case study of all the 5 coil pair. So mutual coupling is measured using LCR meter and using your analytical calculation, and then there is percentage error. So we can see, so from plotting the mutual inductance of all the coil pair, we see that error decreases with increasing distance between coil and each coil pair. So if air gap is large, the error between our analytical design calculation and actual mutual measured using LCR meter is reduces. And also saw that out of all the geometric characteristics, the inner diameter most affect the accuracy of the analytical expression. Third point, we noticed that analytical expression is highly accurate if distance between coil is greater than minimum size of either coil in the coil pair under test. Right? So let's say your coil pair outer diameter is let's say 1 centimeter, then your analytical expression will be accurate if you are measuring the mutual inductance at air gap of distance greater than 1 centimeter, like that. So, and trend of variation, however, you will notice is same. So analytical expression is not highly accurate, but it does give us a confidence because we see that the trend of the variation of the mutual inductance with air gap is at least similar to the trend predicted by our LCR meter. So we cannot entirely rely on our LCR meter analytical expression. So this is the challenge with designing our planar inductor. Now this is just the inductor part, right? We have only designed, calculated the number of turns, inner and outer diameter. But what about the ferrite spoke, right? Again, if we add ferrite, those expressions we cannot use. So in the end, you can start with the analytical expression to get a nearby value, and fine tuning you have to do it in the some kind of FEA tool such as ANSYS, right? Because obtaining a closed form analytical expression is simply too difficult. Even if you obtain it, it may not be highly accurate because of the nature of the geometry of the coil. So let's understand what is flux cancellation and negative mutual inductance. So this is a plot of mutual inductance versus misalignment. And misalignment means, let's say this is your receiver and this is your transmitter. So if both axes are perfectly aligned, we say that misalignment is zero. Now, if your transmitter is here, axis is here, but receiver is here, and both axes are not perfectly aligned. There is some displacement. So this placement is called misalignment, right? So distance between these two axes will give you the misalignment in the terms of centimeter or millimeter and so, right? So if you plot the mutual inductance versus misalignment, you will see that after a certain value of misalignment, your mutual coupling will become zero, right? And this mutual coupling, the misalignment position at which mutual coupling becomes zero, we call it null for the wireless power transfer. And position of this magnetic null changes with the air gap between the primary and secondary coil. So while designing, you can plan carefully your design for a given air gap. You can design the outer inner diameter in such a way that you can shift the magnetic coupling as far as possible, right? So you get a wide charging out of a given coil. So again, this is a design challenge because one would ideally want a charging coil which can give a wide charging zone. So there are a lot of factors to be considered. First, we did the analytical calculation to get to a nearby value of the inductance. Now we have to fine tune in the ANSYS. We have to add the ferrite. We have to add the shielding. And then we also have to take care of this magnetic null. We want to keep this magnetic null as far as possible. So we get a very, very wide charging zone out of our coil unit. So why this magnetic null happens, we can understand using this conceptual diagram. So let's say this is the cross section of our primary coil. This is the cross section of secondary coil. So primary coil, when excited by alternating current, we have alternating flux, and which will obviously have this kind of overall shape, right? So flux generated from the primary coil will intersect the secondary coil in this way. It will intersect the bottom surface, and then the returning flux will intersect the top surface. Now, both component of this flux will generate the induced EMF in the secondary coil in opposite direction. Which so EMF induced by returning flux will cancel the EMF induced by upward going flux. So once they are perfectly aligned, we can see most of the EMF induced is by upward going flux, and very few flux component are intersecting the secondary coil from the top, right? So magnitude of the EMF induced by both the component is not equal, and therefore we have net induced EMF in the secondary coil. But let's say your secondary is misaligned like this here in this picture. So some of the flux are now intersecting from the bottom, and it may be possible that for a particular misalignment, same amount of flux is intersecting from the top. So induced EMF, net induced EMF will be zero. And during that particular misalignment, we get magnetic null, which we also call as flux cancellation, because the flux itself is cancelling. Upward going flux is cancelling the is cancelled by the returning flux. And then finally, after certain misalignment here, none of the upward going flux intersect the coil, right? And only returning flux intersect. Then you have induced EMF in a opposite polarity. So your mutual inductance become negative. And this we observe in the plot also. So here, if you see, the mutual inductance is less than zero. So it's negative. And then after certain misalignment, it becomes zero. So first the coupling becomes zero, then become negatives, and then it becomes zero. So that's the explanation why you will see that when you are designing the coil, you will see the negative mutual inductance also in the calculation, and this is the way to explain it intuitively. And this you can observe in your FES simulation, the flux line you can observe. So this is the flux line of two coil of a coil pair in perfect alignment. You can see most of the flux line are intersecting from the bottom. So obviously it's a perfectly aligned condition. You have the maximum induced EMF in the secondary. And here is the cross-section view when we have the misalignment, and you can see upward going flux does not intersect, right? One line flux line where we are seeing is barely touching it, and then you have the returning flux. So at this particular instant, ANSYS was giving negative mutual inductance. So this is how you can observe that intuitive explanation in some FUT. Right. Now, once we have designed our done our analytical calculation, design our coil in the ANSYS, now it's time to fabricate. And for fabrication, obviously, now SAE has J294 has defined the standard that wireless chargers should operate between 85 kilohertz to 90 kilohertz or 83 kilohertz to 90 kilohertz switching frequency or resonant frequency. Right now, this is a high frequency. So there will be losses in the conductor, not just the conduction loss, but we will have the high frequency effects such as gain effect and proximity effect. So we cannot use just any wire. We need Liz wire. So Liz wire are multi-stranded wire, and difference between this multi-strand wire and a normal wire, normal multi-strand wire is that in Liz wire each strand is insulated from each other. Right, and they are twisted in such a way that they cancel the effect of proximity effect, or if not totally cancel, it will reduce it to a significant. So let's say our charger requirements is that 30 ampere is the maximum current which could which would flow in our charger at rated load. Right, so we can calculate the overall gauge of the required wire. So area of cross section of wire is calculated by current density. So you can pick a current density depending upon your thermal management system of the charger. If just a air cooled, you are not using any kind of forced cooling, using for fan or let's say some kind of liquid cooling, then 4 amp per millimeter square is a good number to start with. And so we using this 30 amp and 4 amp per mm square of current density, we get the cross section of 7.9 mm square. Then using the AWG American wire gauge chart, we can select either 9 or 8 AWG gauge, right? So let's we select 8 AWG, right? Now we have to calculate the strand diameter of the Liz wire. So this is the overall cross section of the wire. Now, how to calculate how thin should be one strand? So for that, we see the resistivity of copper, right? So we have to calculate the skin depth for a particular frequency, right? So this is the formula for skin depth, and we select the depending upon you are using copper wire or aluminum wire, you will get this formula of skin depth. And let's say you got using this formula 1 mm, then you select a strand which is 2 or 3 factor less than this 1 mm. So 1/3 mm of a strand diameter, like that. Now you have the diameter of one strand and you have the diameter of overall wire. So you can calculate the number of strand you will need. So like here I mentioned, good design uses strand diameter smaller than the skin depth by a factor of 4 or more. Okay, so therefore a strand of 38 AWG diameter is selected. Okay, so number of strand you get is around 1044.7, which is 1045 strand. Now you have calculated the number of strength, overall gauge of the wire, but that is not enough, right? Especially you are designing a very efficient system. Especially if you are designing a very efficient system, you need to consider the skin and proximity effect. So there are two kind of skin effect. One is at the strand level and one is at bundle level. And then again you have the proximity effect at the strand level and bundle level. So simple twisting, let's say you have the 1000 strand and you twisted the wire, right? Then simple twisting is adequate to eliminate the strand level. But to avoid bundle level skin effect, you need multiple level of twisting. right? So, and this is how it's done. First, you calculate n1 number of strands which could be twisted together, followed by twisting of n2 number of those sub-bundles and additional stage if required. So, for example, the value of n1 you can calculate using this. So, this is the formula given by the manufacturer of the lease wire itself. So, this is the formula, and by using this formula, we calculate that we should have 42 strands. We should have one bundle of 42 strands. Now, we make the bundle of 42 strands, right? So, for the second level, 5 bundle of this 42, one bundle made from this strand is used. So you have total utilized 210 strand. Now for the final stage, again 5 bundle of this particular bundle is used to give you 1050 strand which you calculated. Now you need to go to the manufacturer data sheet, and if you can find a lease wire which meets your requirement. If it doesn't meet, you can contact them and they will manufacture it for you. Right? So for 30 amp, overall diameter of the wire was 4.6 mm. Obviously, this is all the strand has coating. They are in varnish coating to insulate it from each other. So this is not the diameter of a bare conductor, and it will be obviously a little bit higher than a normal wire of that particular current rating. Now, another important thing or issue with design of wireless charger is bifurcation. Now, we saw that this was our topology, right? Series topology. Let's say it's a series parallel or parallel. It's a multi-resonant topology. So primary side have one resonant tank and secondary side have another resonant. So let's see the case of series one, because this is what we have picked for this lecture. So in a series, we have 2 resonant tank, right? So for such resonant tank, you have more than one resonant frequency, and that causes the issue because you have one true resonant frequency for which you have tuned, and then there are 2 other resonant frequency which happens to exist when your coupling is above a certain critical value of coupling, right? So you can see this blue trace is for let's say there is some critical coupling Kc which causes this one resonant frequency to split into 3 resonant frequencies. So below this critical frequency, I have plotted this curve for 0.6 times Kc. So this blue trace, here you can see there is only one peak, right? This is the voltage gain versus frequency, and which is happening at 40 kilohertz, which is the true resonant frequency. And another plot is for 0.8 Kc, 0.8 Kc, again less than critical coupling. Here you will see that your frequency is your peak is reduced, and there you can see there are almost you have 2 peaks, and one you have a kind of draw in the middle. And then for coupling higher than this critical coupling, you can clearly see that you have 2 peaks and 1 valley, which is very pronounced. So as K increases above Kc, right, voltage gain decreases and resonant frequency is split into 3 frequency, which you can compute using this formula. So one is FL, one is FH. So FH would be above the true resonant frequency, and FL will be below the true resonant frequency. And you can observe this in the phase gain plot. So you have the input phase angle versus frequency, and for the blue, you can see you have only one resonant frequency. For 0.8 times, still you have only one resonant frequency, but you can see it is starting to divert from the linear shape. Now for greater than Kc, you have this input phase angle crossing this 0 phase angle 3 times. One time here, and another time. So these are the three resonant frequency, and this is problematic because your controller, if you are using variable frequency control, might get confused during the load change. It might, instead of operating the converter to 40 kilohertz, it might operate it to the FH or FL, and which will affect the performance of your chart. Right. So how to handle this by design? One is by handling using a control. In control itself, you can write the algorithm to identify the true resonant frequency, which will occupy a memory in your SoC, right? Your microcontroller, which you are using for the control. Other way to handle is by the design itself. So you can design a charger in which you can ensure, let's say you have designed a charger for electric vehicle. Now, like I said, in electric vehicle, your receiver is mounted underneath the vehicle, right? And transmitter is on the ground. Now, there is a ground vehicle clearance required by the law, which could be, depending on country to country, it could be anything between 10 to 15 centimeter, or 10 to 15 to 20 centimeter. It depends upon country and type of vehicle. So for passenger vehicle in USA, I don't have the data for India, how much is the ground clearance vehicle required by the law. But in USA, it was 15 to 20 centimeters. So if you are designing a charger, you have to ensure that your coupling is optimum between these two air gaps. Now, obviously, for a vehicle, let's say this is the vehicle, air gap will be fixed, right? Only slight difference will be during loading and unloading of the vehicle. If the vehicle is fully loaded, there will be a little bit pressure on the chassis and the air gap will slightly reduce. But you know the minimum air gap it can go to. So you can design in such a way that in your operating range, your coupling remains below the critical coupling case, right? So one take away from this design is that in a normal transformer, normal inductor, we desire high coupling, but in the wireless charging, higher coupling is not desired, right? And one might argue, but higher coupling should improve your efficiency, but that is not the case. So here is the plot of efficiency versus coupling coefficient for a series topology. You can see, yes, up to a certain value of coupling, your efficiency does increase, but after a certain value of coupling coefficient, your efficiency is not affected by coupling coefficient. So, and this is, you can verify analytically also. So the K is here in the denominator, and after a certain value, this will become negligible, and all you are left with is RL by RS plus RL, which are the load resistance and the parasitic resistance of the coil, and which are fixed. So you cannot go above a certain efficiency, even if you increase the coupling coefficient. But instead of increasing efficiency, you will not get efficiency, but you will risk this bifurcation, which might destabilize your control. So here is just a example of wireless charger setup. So here this is a design. This was designed by me. It's a charger, it's a transmitter which is supposed to be a receiver which is supposed to be underneath the vehicle, and this is the transmitter which will be on the ground. Here is the top view, and the air gap is fixed to 60 centimeter. And now, even if the vehicle is fully loaded, it was observed that the change in the air gap would be 15 centimeter, 1 centimeter. So, and this is the lease wire. This is just to show you fabrication of the coil, then measuring the coil inductance and mutual inductance using LCR meter. This shows the ferrite spoke to minimize the leakage flux. And this is the high frequency inverter to generate a 40 kilohertz square wave signal to power the. And this is the whole setup of 3.6 kilowatt charger, which is WPT1, right? This is the performance analysis of the charger. Overall diameter was 522 mm, or you can say 52 centimeter. Is overall half meter pad. So this is almost half meter. ferrite scope to minimize the leakage flux, and we also measure the magnetic null. So magnetic null occur at 37 centimeter of misalignment, which is 70% of overall parameter. So we go above 40% of magnetic null by carefully designing the charging pad. This is the efficiency during CCCV charging mode of a battery pack. And here we can see that DC to DC efficiency of design charger is 91% and then rated load condition. And this is DC to DC efficiency. If we add the front-end converter stage and the state-of-the-art front-end converter stage operates with 98% efficiency, then we can get overall efficiency of 89%, which is what you get from a plug-in charger also of a similar rate. So in paper, you might read that somebody designed a charger which is operating at 98%, 99%, but that is at one particular load. It is not, the same charger cannot operate at the same efficiency throughout the charging profile. So that data is obviously misleading. This is the very true data which you get from your conventional plug-in chargers. So it's comparable to your plug-in charger, right? So obviously efficiency little lesser side because plug-in charger, tear down of plug-in charger, if you read on the internet of 3 kilowatt, they have calculated to 92% in some cases or 93% even, right? But still very much comparable. And this is the, let's say this is your car and some passenger standing here, coil is there, he should not get exposed to the magnetic radiation or magnetic field, right? So you can study this in the ANSYS also and you can calculate how much of the leakage flux here, whether it is within the limit prescribed by the standard organizations such as ICE, IRP or IEEE, right? And this shows the performance of the controller and the different loading and mutual coupling conditions. So charger 3.6 kilowatt power transfer happens with much with desired performance, you can say. Now another key aspect is the foreign object detection. Now, what is foreign object detection? Let's say you have the transmitter coil which is installed on the parking lot or in your home in the garage. So let's say you dropped your keychain or a coin accidentally, and your charger is active, right? So your car is charging, is parked, is charging, but you dropped a coin or some metal object, right? Now, obviously there will be eddy current induced in the coin or that metallic object, and which will heat the coin, right? And it becomes so hot that it can compromise the integrity of charger itself. It can also harm your pet, or even a person, if let's say you went to pick ahead that coin without realizing it's hot, it can harm you also, right? So and it can also interfere with the charging process, right? So we need to detect such thing which can hamper the charging process or which can interfere with the normal working of the charger. For that purpose, we need foreign object detection, right? So here is one example. Let's say we drop a 10 gram of copper coin on the charger, and we can calculate the temperature rise using this formula where delta T is the temperature, Q is the energy, M is the mass, and Cp is the specific heat. So for 10 gram, an eddy current loss in the object is 0.5 watt. We see that temperature rise in the coin for 1 minute would be 7.79 degrees Celsius. And for 10 minutes, obviously 77 degrees Celsius, which is too hot. Charger itself is hot because it's charging the vehicle, right? It's transferring 3 kilowatt of power. So obviously you have designed it to operate it for certain maximum temperature. And on top of that, you have this much heating, which can damage the charger itself. It's not sealed properly. If its casing is not good enough to tolerate that, or this heat can damage your person or animal who comes in contact with that. So there should be some mechanism to detect and signal the transmitter to stop charging because there is some foreign object on the coil. So there are different ways to do that. And then first one is most basic, the sensor based, where you use the temperature sensors, thermal camera, radar, or pressure sensors, such kind of thing. But these are expensive, right? So it increases the cost. Another is the sensing pattern based detection, in which you use this detection coil, which is some cage like this, which is overlapping your transmitter coil. And now say some foreign object is fall upon this sensing pattern, then it detects the change in the induced voltage in this sensing pattern coil, and by detecting the change in the induced voltage, it can signal that there is a foreign object which needs to be removed, or it may interfere with the charging process, or it may be harmful to some person who unintentionally pick it up. So it can detect both metallic objects and living objects. So it can do living object detection also, right? It has some limitation because it has blind spot. Obviously, there is blind spots, and so it cannot detect foreign object of all the sizes. So that's the demerit. Then there is system parameter based detection, and it does not require any sensor, but it monitors the variation in the current and voltage and self-inductance of the charger itself, and by that it signals. But these things could be, this thing could also vary by some other factor other than foreign object detection. So there should be some mechanism to differentiate between that. So this is one key area of wireless charger which is still under research, right? And so what are the main challenges in the foreign object detection? So we need some kind of foreign object detection which can detect metal object as well as living object. So essentially, we need a universal foreign object detection. So some foreign object detection systems are applicable for certain coil shape. But what about a module which we can install it on all coil shape of all charger of all, utilizing different concepts, right? So we can call it a universal foreign object detection, which can detect foreign object in coil of every shape, right? So these are the challenges which are yet to be solved. Now let's go to the control technique. So in control, you can control the charger from primary side, you can control from the secondary side, and you can control from the both sides or dual side. From the primary side, you can use variable frequency control or fixed frequency control. And in the fixed frequency control, you can do duty cycle control, or you can use front-end converter control, where you use it to vary the voltage input to the inverter. Now, secondary side control, you have the active rectifier, right, which is essentially rectifier with instead of diode, you are using MOSFET or IGBT or some kind of control switches. Or you can have one DC to DC converter stage, which varies the output voltage or current generated by your rectifier stage. So let's understand different control techniques using one series topology example. So here, this is what essentially we are trying to charge the battery, and we are controlling the battery current and battery voltage. Now we know for lithium ion battery, CC/CV charging mode is used, constant current, constant. So essentially, we are trying to control the battery current and battery voltage. Now this battery current and battery voltage is being drawn from this secondary coil, which is coupled to the primary coil, which is drawing it from your DC supply and so on. So to control, we have lots of options. We can directly control this battery voltage and battery current, right? By having one extra converter stage, or we can control from indirectly by controlling this IES and VS, because there is direct mathematical relation between those two, or we can directly control by controlling this VP and IP, or we can control using this sides, right? So there are number of control variables. So from primary side, we have primary current, primary voltage. By controlling these two, we can control the charging of the battery. From the secondary side, we can control these two variables. We can also directly control battery voltage, battery control, or we can also control using our DC link voltage and control by varying that, right? And each has its own merit and demerit. and complications. All those methods will require the same charging algorithm if we are going for the CCCV charging mode. So first we need to charge the battery using some constant current until its voltage rises to the rated voltage. And then we switch to the CV mode. In that, voltage is maintained and current is allowed to freely flow. Obviously, it will decrease and becomes becomes as low as charging progresses, right? So you have the CCCV charging mode, and here is one logic to generate the CCCV charging profile. So mainly we have two type of control: direct control of battery charge. So we sense the I bat and V bat, we directly feed it to our controller, or indirect control, in which we don't sense the battery voltage and battery current. Instead, we sense the resonant tank voltage and current, or DC link voltage and current. And how do we regulate the voltage? So let's say you have a primary side inverter, it's a resonant converter. We cannot use a regular PWM like sine triangle PWM. So we use different kind of PWM techniques, such as voltage cancellation method, which could be symmetrical or symmetrical voltage cancellation, or a symmetrical duty cycle, or popularly symmetrical voltage cancellation is used. This kind of waveform, which you have seen, this is also called phase shift control, right? In which we control the voltage, control the phase shift between the voltage generated at this node and this node, or two leg of the meter, right? So here are the three popular techniques for controlling the output voltage of the inverter. This is the phase shift. It's also called symmetrical voltage cancellation. Then you have the asymmetrical voltage cancellation, because the voltage is asymmetrical in shape, right? And then you have the asymmetrical duty cycle. Out of all the three, this one is the most popular, where you have full control of the voltage. You can go from 0 to 100, full 100%, right? Whereas there you can only go from 50% to 100%. You cannot go fully 0%. And here again, you cannot go fully. You cannot go to 0. Right? And again, another factor is zero voltage switching, to minimize the switching frequency, switching losses. And this is a logic circuit to analog circuit to generate those PWM, popular PWM techniques. You can generate digitally, you can generate using analog circuit implementation, right? So this is the phase shift, this is the asymmetrical voltage cancellation, and this is the asymmetrical duty cycle. Now this is a conceptual diagram of how primary side direct control works. In primary side direct control, you can have a DC to DC converter controlling the DC input voltage, and by that varying the DC input voltage and DC input current. By sensing battery voltage and current as a feedback signal, you can control the battery charge. Similarly, you can instead of controlling this front-end converter, you can control the inverter, right? You can regulate the output voltage, and which in turn will give you the regulated battery voltage and current. So this is the primary side direct control. Now you have the secondary side direct control, in which direct control means you are directly sensing the battery voltage and current, and then you are controlling the secondary side, the converter. So you need to use active rectifier, or you can use normal rectifier, but a DC to DC converter stage. Then you have dual side, in which you can control both the primary and secondary side. This is very ideal for necessary for the bidirectional power transfer. This is an anti-spice simulation of a 100 watt charger meant for low power application or consumer electronics application. And here you can see we have the CCCV charging. So this is the series topology, and this simulates our lithium polymer battery. This is the phase shift control PWM modulator, and this is the PI controller to detect between the CV mode and CC mode. And here we get the CCCV charging profile. The blue trace is the constant current, and green trace is the battery voltage, which is rising. And once the battery voltage reaches the rated voltage, which is 21 volt, we switch to the CV mode, in which battery voltage is maintained constant and current is left to freely vary, which will obviously decrease. And you can notice throughout charging process, your equivalent resistance of the lithium polymer battery will increase non-linearly. And only at one particular instant, when you are switching CC to CV, you have the maximum power transfer. Right. So that's why efficiency of the charger is not fixed. It's varied throughout the charging process. So when somebody says that your charger has the efficiency of 99%, you should also add that's the maximum peak efficiency. It's not that the charger will be operating at that efficiency for the charging process. So you have the indirect control also, in which you are not sensing the battery voltage and current, but you are sensing the resonant tank voltage and current, and then you are controlling the primary side converter or the secondary side, like that. So this is the implementation of indirect control in the Plex. Here we are not sensing the battery voltage and current. So this is the lithium-ion battery model, and instead we are sensing the primary side current, which I am using as a feedback, and primary side average voltage as a feedback, and then controlling the battery voltage and current. And here it works just fine. And so this lecture essentially covers the design of magnetics part and overview of different control techniques which you can use for the wireless charging. So I'm done with the lecture. If you have any question, feel free to ask.
Thank you, sir, for your enlightening lecture. We deeply appreciate the time and effort you have been taken to share your valuable knowledge with us today. Now I request a participant, please ask the question, and you can also write in chat box.
Okay, I guess there are no questions.
Participants, if you have any question, please unmute yourself and ask to sir.
Participant, is it any query? Nitin Anand? Is it any query? Then ask.
Hello, sir. Good afternoon.
Yes, good afternoon.
Sir, the session was very nice. I have just a general query. Sir, as you told in the slides that the most of the power is not transferred from the primary side to the secondary side when we are using the coil. So most of the power is being lost. So we are using some shielding process regarding that, sir.
Most of the power is lost.
Yes, sir. In the actually, we are in the slides. It has been told that the power is not being totally captured, and most of the power is lost due to the air gap.
Yes, for that we use the resonance, right?
Yes.
So that's why we are adding compensation capacitor to compensate the effect of poor coupling.
Sir, only these methods are only suitable, or we can use some of the shielding process also in that. So in one of the papers, we were we have studied that we use the shielding process like active shielding and the passive shielding in order to recapture the energy which has been lost in the air gap.
Yeah, up to a certain extent, but still you need compensation, right? And when you add compensation, it is most effective, right? Because the your inverter is only supplying the losses which any converter will have in terms of your copper loss through the wire and all, right? And the energy is freely oscillating between your capacitor and inductor. So energy stored in the inductor comes from capacitor and vice versa. So essentially, this is the most effective way to minimize the losses due to the poor coupling.
Okay, sir. So apart from compensation techniques, are there any other methods by which we can increase the efficiency of the system?
I don't know. None that I'm aware of.
Okay, sir. So thank you so much, sir. Thank you, sir.
No problem.
Thank you, sir. Kumar sir.
Thank you.
Dr. Nadeem is there. Maybe there is no query. There is no query for chat box. So thank you, sir, for on this topic.
Thank you.
Hello.
Yeah, I can hear you. Thank you. Thank you.
Is it
for
audible?
inviting
Kumar
me.
sir.
Yes, I can hear you.
Yeah. So thank you, sir.
Yeah, thank you. Bye bye.
Thank you, sir. So shall I start next session?
Yeah, I'm asking for expertise.
Okay, sir.
Rakesh, sir.